I'm Christine, I'm from Honeycomb, and today I'm taking you under the hood to talk a little bit about the design decisions that went into building our storage system. I feel like it's a fairly small group, so if you want me to clarify any points along the way, feel free to, I'll pause a couple times, but otherwise also just feel free to grab me afterwards. Cool. So for anyone who's not familiar, Honeycomb is a system that combines the speed of time series with the raw power of rich events. We've built a tool for engineers, by engineers, for the interactive and iterative debugging of systems. What does that mean? Honeycomb came out of our experience at Facebook with the acquisition of Parse, where Parse had hundreds of thousands of different apps running on our platform. And prior to coming to Facebook, it was next to impossible to debug anything on demand. We had our pre-aggregated ganglia graphs and our logs in S3. And what would happen quite often is we'd be looking happily at our graphs. They'd be green, they'd be great. The error rate would be low. And a customer would come to us and say, Parse is down. And we'd go back to them, and we'd go back to our graphs, and we'd look at it and be like, no, everything looks fine. You guys, can you check your Wi-Fi? And there'd be a back and forth, and ultimately we'd have to go digging or something, because when your system is processing thousands, tens of thousands, however many requests that are fine, that are doing fine, it becomes really hard with things like ganglia or pre-aggregated metric systems to tease out the one app that's doing 3 requests per second that's failing every time or hitting a timeout each time. And this sort of breaking down by a high cardinality attribute, this either looking at the top 10 customers that were hitting something or scoping everything by one customer and then doing the normal, P99s and averages and such, we really needed to be able to nail this high cardinality breakdown use case. And so when we got to Facebook, Scoobo was basically a system that suddenly gave us the flexibility to dive in and explore any of these different cross-sections of attributes that we might care about. This one app, iOS requests just from that app, but iOS requests on this version of the operating system hitting this endpoint. We also really fell in love with the ability to ask questions and have each kind of, could this be the source of the problem? Have each of those be answered in a matter of seconds rather than minutes or hours. You don't want to be wasting time waiting for Hive to get back to an answer if you're like, I'm not even sure if I'm looking in the right place. I just need to start ruling things out. And we loved that Scoobo let you basically satisfy this. Well, what about this? What about that? Could it be this? This natural human querying pattern. And Scoobo, a little bit about the history, is it was initially built to help debug MySQL performance regressions, and then grew and grew to be useful to lots of different groups all over the company. Anyone that essentially needed to do this repeated ad hoc, let me look under this rock, let me look under that rock for the problem. So upon leaving Facebook, we were appalled to realize that this system didn't exist in the wild, because we knew how valuable it was for platforms like us. And because we'd used this tool, we knew what sort of experience we wanted to provide. We knew the value of certain interactions, and we knew the sorts of things that would be required to build and provide that experience. And we were sort of researching some off-the-shelf options and ended up building our own Datastore with these goals in mind. So it is normal for read time aggregation is a fancy way of saying basically what log aggregators and normal databases do. But it is not normal for metric systems that are super write optimized, things that have orders and orders of magnitude more writes than reads. Again, high cardinality breakdowns and filters are bread and butter. We can't open ourselves up to the same sorts of practical problems that pre-aggregated systems try to do when you're trying to store individual breakdowns of every single possible combination of app ID and platform and operating system version and app version and so on and so forth. We also really believe that context is important because while yes, you should sort of know your data. You should sort of know where to look for problems. Nothing can replace the experience of being able to look at a spike and be like, okay, well, what is actually happening there? What are the actual events that are causing this without forcing a human to go and kind of cross-reference two graphs to see which one spiked at the same time? And raw rows, again, the origin of Scoobo, raw rows are crucial for understanding things like database query patterns. If you can't get down to the raw query, you're basically hamstrung. We also believe that good tools get out of your way and let you get your job done. So engineers should be able to add new fields, should be able to debug, realize something is missing, add something else, redeploy, get new data, without having to go through extra steps to update the schema, build indices, wait for things to become available. And we shouldn't have to suffer degraded performance if you're sending events and they're not all perfectly aligned in the schema. If not all columns are filled. If maybe it doesn't make sense to track something like the operating system version if you're only looking at an API hit versus something from a mobile device. Who knows? But this sort of flexibility, this sort of devotion to the value of sparse rows actually makes it really difficult to build a system that relies on maintaining indices if you can then have an arbitrary number of columns of widely varying importance and varying based on the person looking at it or the time that you're looking at it. We wanted it to be fast. We wanted to be able to get you answers quickly. This often, in simpler metric systems, this often means storing something in a pre-aggregated form. Great, you do all the work on the right path, reading it out is really simple. Awesome. Except, tied to our first goal, this really means that we had to build a column store. We had to build something that would let us work with this analytical workload, but not rely on doing all the work ahead of time. And here, best effort availability means that we believe fast and mostly correct is way better than slow and 100% correct. When you're up in the middle of the night trying to figure out why your service is down, it's okay if 5% of your nodes aren't, or 5% of your storage nodes aren't responding because you'll see the general shape of the data, you'll see the trends, you'll see what's going on. Near real time basically is talking about the low latency between writing something to Honeycomb and having it available for reads. Again, we're building for infrastructure engineers and on-call use cases. So if the storage solution has like a several minute delay or an hour or God forbid a day, it's not something that's going to be useful for this use case. And finally, unlike Facebook internal tools, we cannot just put everything into memory and throw money at the solution yet. All right. So how does that translate to actually thinking about the ingestion pipeline? We started off essentially optimizing for simple, straightforward, and fast for us to build. We're a small startup trying to get something out the door. So in a lot of cases, we made the simple solution that would leave room for optimization, but minimize as much, prevent as much over-engineering as possible. Fast, again, write optimized, lots more writes and reads. And while we can't do everything in memory, dropping costs mean that we can store things on SSDs. And then we can start taking advantage of file system operations to do things like age out data or clump things and ask the operating system to take care of flushing and removal. Okay, so remember these things I've been saying about best effort availability apply only to the read path. The write path, we want to be as available as possible. So the API server's goal is as quickly as possible to do authentication, figure out which data set we're talking about, do any sort of rate limiting, updating schemas, but as quickly as possible, dumping it into our first persistent store, which is Kafka. The API also, when I say updating the schema, it essentially converts a JSON blob that you hand us into a self-described event. So the event then knows about things like what my column IDs are and what my dataset ID is. I want to talk a little bit about how we use Kafka. We essentially assign, datasets are assigned to one or more partitions. And so when an event comes in and the API server is ready to write it into Kafka, it picks one of the partitions randomly and writes it straight in. And each Kafka partition is consumed by a set of storage nodes. These storage nodes keep track of which partition they're assigned to, and essentially just constantly consume from that Kafka partition. And they also keep track of which Kafka offset to start reading from. So they actually manage checkpointing and kind of offsets themselves. For a given event, we identify the dataset ID, 42, timestamp. Everything has a timestamp coming into the system. We optimize for real time and recent time. So we age out data fairly aggressively. And we identify the columns involved. Incoming events describe themselves. So everything that is in here is all that's necessary to figure out where to put these incoming blobs. The storage node then maintains a set of appenders across which these columns and these values are basically broken up and transmitted, stored, not transmitted. Each column file, which is a column here, individual records hold an index and a value. So one thing that holds true in our system is that everything has a timestamp. So our timestamp column essentially serves as an index into the other column files. And we flush periodically and split the data into segments. Essentially chunking the stream into pieces roughly by time, really by time ingested. The periodic flushes also give us the chance to maintain metadata per segment. So things like the minimum and maximum timestamp of data contained in this thing, as well as the last index and Kafka offset written to disk inside that segment. And finally, we also do a periodic checkpoint, like I mentioned, to track the Kafka offset that we know, that we guarantee has been safely flushed to disk. So, things you may notice. We don't have any indices to maintain on the write path. This means that you can go from sending 10 columns to 20 columns to 50 columns, and we're just gonna do them all in parallel. There's not additional writing to do on top of that. We don't have any compaction or compression right now. Our column files are essentially written as compactly as possible, and we absolutely could put in whatever compression optimizations we want. The door is wide open for that. We have actually started some compression, but we're intentionally leaving it open and kind of seeing how things flow. As I get my 10-minute warning, are there any questions about ingest before I jump into reads? Cool. All right, so reads are exclusively driven by our web UI at this point. So reads are currently being issued only at the speed of humans. Again, one of our goals for this flow is designing this in support of handling very wide events, ad hoc querying, and really optimizing for performance given the ingest patterns. Approximation algorithms are also really great, have gotten really great, really low margin of error where large volumes of data are involved. So we approximate wherever possible. We try to make it clear to the user that that's what's happening underneath. Again, it's 3 a.m. You probably care about whether it's 95 versus 5 a lot more than if it's 95 versus 93. Query results are also cheap compared to the volume of the raw data stored. And so one of the things that we believe, sort of just a sidebar, is that permalinks to graphs should be permanent. It's incredibly frustrating to have done some work and saved it somewhere, and then 2 weeks later gone and try to view some graph, some example of a postmortem, some example to use in a postmortem, and have the data gone underneath your feed. We also sort of want to find a way to sidestep the sort of thundering herd of humans problem of something like ELK, where sharing a link to a query then causes everyone who views that query to rerun the query and possibly hurt your cluster. Okay, the good stuff. So when a query comes in through the web UI, we do the translation from names to IDs, and we use service discovery to figure out which storage nodes correspond to the partitions that make up the data set. Here, apparently, I've decided that there are 5 partitions that this data set is stored in. And so we choose one node for each partition, one replica for each partition necessary to pull data for this data set. We randomly choose a root node. We pass the query and the child nodes down to this root node. And the root node fans out to other nodes as necessary. So each node runs the query locally and essentially builds intermediary data structures. Inside each leaf node, first we use that segment data that I mentioned to figure out which segments we even need to look at. If we can avoid reading entire chunks of data off disk, awesome. We basically use the metadata to filter them out. Once we identify that a segment is interesting to us, we use the TimeBound, which has disappeared, but is in the right-hand corner. We use the TimeBound to figure out which timestamps we care about, which indices inside this segment are interesting or even qualify. Once it's past the time filter, we then look to see if the query has any other filters that we can use to, again, slash data out that we don't need to look at. So here, looks like we're filtering on the method. So these other two, these two values pass, and only then do we start reading the value from the column necessary to actually produce an answer. So once the leaf nodes each have the answer to their query, they hand them back. The parent node at each level is responsible for timing out slow children, as well as merging these intermediary structures. This sort of fanning out can happen at multiple levels. There are thresholds that determine how many nodes to include at each level. And the root node finalizes or coalesces the results, spits it back to the client. And along the way, dumps the results in S3 for good measure, just so that folks never lose the actual work that they've done, even if the original data ages out. So a number of the things that, some of the themes of designing this system is that we always believe availability and speed are better from the perspective of the user. I don't want to say this is categorically true, but almost anywhere we can make that trade-off. We would rather kill a slow node, time something out, and tell you, rather than falling over or waiting an extra few minutes for that one node to tell us that they're dead. A pretty common trade-off for storage systems to make like this is that append only, without any sort of compaction, then exposes certainly certain data sets to bad ingest patterns. Again, this is localized to just the data set that someone is writing into, but with one of the things that I've mentioned a bunch is essentially using time to cull uninteresting segments. If, for example, if the user supplies a timestamp, we try to accommodate that, and it can significantly degrade their performance. Optimizing reads is easier than optimizing writes. We lay data down as efficiently as possible and rely on the simplicity of what we've written so far to make it smarter and make it faster to read certain things out. And I'm happy to answer questions, which I hope some of you have, and otherwise I'm happy to talk afterwards about your interest in this space. Thank you very much. Oh gosh. Yes.
So you said that you may have data pretty quickly. What do you assume the average use case is? How much data should your customers keep around?
That varies super widely by the use case and the customer. We essentially let them tell us. There's a lot of, okay, how much data do you actually need to access? How fine-grained does it need to be? Would you consider sampling? There's a number of things that we talk through when we're talking to someone about kind of how much retention they want. would they consider something like cold storage? Would they consider, if they want to go back more than a couple weeks, would they consider waiting a little bit and telling us, hey, load this data back in? There's a bunch of games we can play. So, yeah. Anything else? Cool. Thank you all.